Why JavaScript can touch sockets directly? JavaScript in the browser, it cannot call system calls, syscalls, cannot open raw sockets, cannot bind to ports, cannot read or write Ethernet or IP headers because the browser sandboxes JavaScript for security. Imagine if any website could sniff your Wi-Fi packets, read every TCP or UDP flow, open raw sockets to bypass firewalls, attack local device on your LAN. That would be catastrophic. So the browser sit between you, JS, and the OS like a bodyguard. Your code JS, then browser networking stack, then OS kernel, then NIC hardware. JS only sees high-level safe web APIs like fetch, XML, HTTP requests, WebSocket, WebRTC. These do not expose low-level hardware or sockets. Flow, how data actually gets from OS to browser to JS. UDP or 2C TCP packet arrives at NIC. Wi-Fi or Ethernet card receives radio or electrical signal. Then number 2, NIC DMA to OS kernel. NIC writes packet into memory, direct memory access. Then number 3, kernel networking stack processes. Ethernet to IP, to TCP to UDP, to socket, the multiplex. Then the OS checks its sockets tables, IP, port, protocol. This is the application socket. Example, UDP 443 to Chrome socket ID 7391. Browser process receives packet. Chrome or Firefox networking thread gets the data. EPOL/KQ/IOCP to browser networking code. FIP, quick or HTTP or /2/HTTP parsing happens in user space. Browser implements quick framing, TLS 1.3 description, HTTP headers, streams. Number 6, browser notifies JS runtime. If you use fetch function, fetch argument code/data then argument resp. Then after the data arrives, browser to JavaScript runtime, which is VB, to resolve the promise to your callback runs. So JS never touch sockets. JS gets only the process result. This explains why JS feel disconnected. Is that why it's hard to understand programming language? Because it's out of touch from the socket? Yes, exactly. JavaScript hides everything. Let data equal await, fetch, argument, code/users. Seems magical. No visibility of NIC interrupts, IP routing, ports, handshakes, packet loss, congestion control. You just get promise resolve to data ready. This make it easy but also makes networking feel invisible. Other programming language are closer to the OS, like C code. Int s equals socket, argument AF underscore enet, sock underscore dgram, 0. Then send to argument s, data, semicolon. This calls a syscall, like what we discussed in operating system. Then send to function to kernel to NIC to var. Python is slightly above that. So for Python, we have sock.send to argument still calls OS sockets. C hashtag, go, rust similar. JavaScript in browsers never reaches this layer. What about Node.js? Node.js can open sockets. Dgram that creates socket argument udport dot send argument because Node is not sandbox. It uses debug to call OS syscalls. Environment, Browser JS can open sockets directly? No. Environment Node.js can open sockets directly? Yes. Environment C or C++ can open sockets directly? Yes. Environment Rust or Go can open sockets directly? Yes. Environment Python can open sockets directly? Yes. So full stack looks like this. Front end, Angular, React, Vue. You have JS to browser to web API to browser networking threads to OS to NIC. For backend, Node.js, Python, Go, C hashtag. You have code to OS syscalls to OS networking to NIC. In OS kernel, we have packet routing, socket tables, congestion control. NIC slash driver, we have hardware frames, interrupts, DMA. The magic is browsers expose a high-level HTTP interface. OS hides the CPU dangerous details. Hardware moves bits. Syntax versus systems. Programming is pure syntax and if-else logic. At the highest level, browser JS, yes, but underneath, C code handles TCP transmission timers. Interrupt handles move packets from NIC to RAM. Scheduler wakes the browser thread. Browser maps socket to HTTP stream. When you write this, const user equal await fetch argument code slash users. Reality is you write one line. Browser plus OS run maybe 100,000 lines. NIC firmware runs even more. So you're seeing only the very top of each machine. Visual summary, JS does not touch the socket. We have a JavaScript code, no syscalls to browser networking, to OS kernel socket to NIC hardware. Why is this hard to learn? Because web developers see only the UI and APIs. 95% of networking is hidden. Real packet flow is several layers below. If you only learn JS, you see logic and syntax but not the system. Once you learn OS networking, syscalls, NIC interrupts, browser sandbox rules, suddenly everything makes sense. Want next? So let's... Understanding TCP or IP illustrated does not automatically make Angular easy, but it does remove a giant invisible wall that most developers never understand. Let's break this down clearly. What each thing teaches you. TCP or IP illustrated teaches how packets move, how sockets work, how OS networking stack functions, Ethernet or Wi-Fi framing, TCP congestion, ACK, retransmission, routing tables, ARP, DH, CP, ICMP, quick/TCP/UDP differences, how NIC drivers talk to the CPU. This knowledge explains what really happens when you call fetch argument code /users in Angular. After reading TCP or IP illustrated, networking becomes not magic anymore, not mysterious. You can visualize the full path from code to kernel to NIC to war/air. But second, Angular is a programming language environment. Angular requires TypeScript or JavaScript syntax, components, templates, change detection, modules and dependency injection, observables, working in browser sandbox. This has almost no overlap with NIC drivers, OS interrupt handlers, or TCP sliding windows. TCP or IP illustrated does not make Angular easy. Angular is still a UI framework with its own rules and abstraction. But once you know networking deeply, you finally understand Angular to browser to OS to NIC to network. And that's a huge shift. Why language feel confusing without systems knowledge? When you only learn Angular, you see things like HTTP.get, argument code /API/users. But you don't know where does this go. What protocols carries it? How does the OS deliver it? What does the NIC physically transmit? So programming feels abstract, symbolic, like memorizing rules with no meaning. Learning TCP or IP fixes this. But TCP or IP is not enough to understand the OS. Do you have to learn some OS plus C like operating system, 3 easy pieces to fully understand TCP or IP illustrated? Yes, if your goal is complete understanding. Because TCP or IP illustrated assumes you know what system calls are, you know processes and threads, you understand kernel or user space separation, you know what EPOL, select, IOCP, or interrupts are. Without OS knowledge, you understand packet formats but not who reads them, who wakes up on interrupt, how socket deliver two processes. Full visibility require three layers: TCP or IP illustrated, network stack and protocols, operating system or step, how processes, syscalls, scheduling interrupts work, basic C socket code, how user program call the kernel, like this: send to argument dot dot dot, then rec v from argument dot dot dot. Once you understand this, everything fits together perfectly. The learning path, if your goal just make web apps, Angular plus JS is enough. You don't need deep OS knowledge. Most developers never learn it. If your goal is understanding computing from Wired to Angular component, then the correct order is operating systems, 3 easy pieces, understand syscalls, processes, kernel, basic C socket programming, understand how application use TCP or UDP, TCP, then third TCP or IP illustrated, understand how protocols behave in real networks. I would also add after the TCP, after the C socket programming, you add data structures and algorithm, and before operating system, 3 easy pieces, you get the computer architecture, which we will discuss later. So after that, Angular becomes just JavaScript syntax and framework rules. Why Angular feels hard without system context? Most beginners learn programming from the TCP, from the top. Angular to JS to HTTP, no idea what lies below. The lower layer feels invisible. Programming feels like memorizing magic keywords. Bug feel mysterious. But if you learn from bottom up, NIC to OS kernel to socket API to protocol behavior to browser sandbox to Angular, suddenly programming becomes logical, predictable, not memorization, just layers on top. Important truth: is programming hard because it's out of touch with the underlying system? Yes, absolutely. If you understand CPU registers, memory, kernel, sockets, TCP or UDP, then learning Angular feels like just a new human language vocabulary. If you don't understand those, Angular feels like a bag of random syntax rules with no grounding. Final answer: does TCP or IP illustrated make Angular easy? No. Angular still needs GS or TS plus framework learning. Does TCP or IP illustrated remove the black box behind fetch? Yes, completely. Do you need OS plus C to fully understand TCP or IP? If you want deep mastery, yes. Why does learning programming feel confusing? Because beginners start from the UI layer, not from the machine layer. So yes, when you don't understand what's happening underneath, JavaScript or Angular, React, etc. can feel like a random bug of syntax rules with no grounding. Let me explain why your brain feel this way and whether learning TCP or IP or C first would fix it. Why learning front-end framework feels floating. When you learn Angular or React or Vue first, here's the mental experience. You're writing code that runs in a browser which has no direct access to the OS, no socket, no syscalls, and everything you do, fetch, DOM, events, is through web APIs, which are already a giant abstractions. So without understanding what underneath, the JavaScript language and framework feels disconnected from reality. Arbitrarily designed, rule-based without deeper meaning, like memorizing vocabulary in a foreign language. This is completely normal. What's actually happening at the lowest levels, machine level? CPU understands registers, memory instructions, interrupts, syscalls. Second, OS level, Linux, Windows, Mac OS. The OS exposes system calls like socket function, read function, write function, connect function, bind function. In C, you can call this directly. Third, browser level. A browser cannot let JS use OS calls. That would be a security disaster. So the browser provides a sandbox and exposes only safe APIs like fetch function, DOM, events, IndexedDB, WebRTC, Canvas. These are implemented internally in C/C++ plus Rust in the browser engine. So JS to browser runtime to OS to TCP or IP to network, which means JavaScript never touches the socket directly. OS handles TCP packets. Browser just delivers data to JS callbacks. Why it feels hard to observe? Because you jump into layer 5 before understanding layers 1 to 4. You're learning Angular component lifecycle, RxJS, browser rendering, TypeScript types, HTTP request, framework rules, but none of that answers what is a request, what is a socket, what is a port, how does a packet even arrive. So the brain has no mental hooks to attach the syntax to. If you understand the underlying machine plus OS plus network, everything in front end feels like magic, and magic is much harder to remember. While reading TCP or IP Illustrated first fix it, it can massively help because you'll understand how TCP or IP works, how sockets communicate, how data enters a computer, how the OS router routes packets, what an HTTP request really is. Suddenly, fetch function is no longer a magical JS function. It's just browser calling OS socket code to OS sends TCP packets to data returns to JS callback files. And that anchors the entire front end stack in reality. But TCP or IP alone won't fully fix the problem. You also need a systems programming language like C or Rust to see memory, pointers, syscalls, how the OS works, how network code runs without a framework that builds foundational intuition. So the usual solid foundation path is computer architecture basics, or first CompTIA A+, then computer architecture basics, operating system fundamentals like OS 3 easy pieces, C sockets plus system calls, data structures and algorithm, TCP or IP Illustrated, browser and web APIs, JavaScript, then Angular/React/Vue. When done in this order, Angular becomes easy, React feels logical, JavaScript makes sense, framework become just tools. So why you're forgetting syntax? Because your brain is doing memorizing without understanding. Humans do not retain that well. You remember ping forever because it is grounded in how network works, but you forget use effect to because it's just an abstract rule with no mental foundation. Real skill building requires doing the work. You already know the truth. You rely on AI to write the first version. Yes, and AI makes you productive, but you learn 5x slower. You don't build mental models, you only get surface proficiently. To deeply learn programming, you need to write code from scratch, debug the errors, make small changes, do unit test, break and fix things yourself. Programming is a motor skill, not just theory. The final formula, if you want to feel grounded and powerful, here's a clean roadmap. Foundation, OS 3 easy pieces, a bit of C, just syscalls plus memory, TCP or IP Illustrated, Volume 1. Systems intuition, understand what happens when you type a URL. That's first. Second, packet leaves your NIC. Third, server receives it. Fourth, app generates HTTP response. Fifth, browser executes JS. Web route runtime, how browser event loop works, what fetch function does under the hood. Then frameworks, now Angular, feels like just functions calling other functions, just high-level abstractions, not unexplainable magic. At that point, syntax sticks, concepts feel grounded, learning accelerates dramatically. Right. So first, local OS networking file like netstat on Windows. We will gonna connect this. Second, cloud networking in platforms like Azure, VNet, public IPs, CIDR, ports, etc. Third, how modern protocols like quick HTTP/3 over UDP fits into all of these. First, on Windows, netstat-ano-pudp, what is happening? Every line like UDP 192.168.1.47 colon 5353 space asterisk colon asterisk space 4148 means a process PID 4148 has opened UDP port 5353. Windows network stock is listening on that IP plus port. When a packet arrives, the NIC receives the packet, the driver signal the window kernel, TCP or IP stack. The kernel looks at protocol UDP plus destination IP plus destination port. Fourth, it finds the matching process from a lookup table. Fifth, the packet is delivered to the process that owns that socket. This is how the OS demultiplex packets. So first, it starts with the hardware, it receives the packet, then the driver or the software for that NIC signal the Windows kernel, then the kernel looks at this protocol UDP plus destination IP plus destination port, which is the socket. It finds the matching process from a lookup table. The packet is then delivered to the process that owns it. So that's the JavaScript callback runtime. This is how the OS demultiplex packet. So yes, every process is effectively registered in Windows with the IP plus port plus protocol tuple. How does this relate to cloud, Azure, AWS, GCP, etc.? The exact same concept applies but with one extra layer, virtualization and routing. In Azure, every VM or app service has a private IP inside a VNet subnet, i.e. 10.0.0.4, maybe a public IP, i.e. 52.20.10.5. The cloud router uses CIDR ranges to decide where to deliver traffic. Example VNet 10.0.0/16. We have subnet 1 app tier colon 10.0.1.0/24. Then we have subnet 2 DB tier 10.0.2.0/24. If a packet comes in, we have 10.0.1.4.10 colon 443 to incoming TCP packet. Azure VNet router first looks at the router's destination IP 10.0.1.10. Second, finds routing rule via CIDR. Third, delivers the packet to the correct VM/app. Fourth, inside that VM, the OS does exactly what Windows did. Look up by protocol plus port, then deliver to the app listening on that port. So the cloud routing is just one level above the OS routing. Third, where does ports matter in cloud deployments? Port matters at 3 layers. Layer A, cloud firewall/network security. In Azure, NSGs, network security groups, Azure Firewall, App Gateway, Load Balancers. These must allow the port, example, NSG rule allow TCP 443 from internet, then traffic can reach your VM/app. Layer B to OS firewall inside VM, Windows firewall, then UFW or firewall D Linux. This must allow the port. Layer C process. Inside OS, your app must be listening, i.e. .NET app.dll. It means opening TCP 443. For NIGS, opens TCP 80/443. Then for SQL Server, opens TCP 1433. If any layer blocks the port, the connection dies. What does CIDR have to do with it? CIDR 10.0.0.0/24, 192.168.1.0/24, etc. is used by routers including Azure VNets, firewalls, Kubernetes, pods and services, subnet divisions. So this CIDR we discussed in chapter 2 are discussed in Azure VNets, which is its routers and its firewalls, its Kubernetes pods and services, and subnet definitions. CIDR determines which network a packet belongs to. Example, request comes in for 10.0.1.45. Azure checks routing table 10.0.1.0/24, meaning app subnet, then forwards packet to that subnet. Inside the VM, the OS then does port-based demux, just like NetStat. How QUIC fits into this? QUIC is UDP based, runs on port 443, used by HTTP/3. So instead of client to TCP 443, it may instead be client to UDP 443 QUIC. But everything else is the same. Cloud layer, Azure sees a UDP packet destined to public IP colon 443. If firewall/NSG allows UDP 443, the packet is forwarded to the VM/app. VM/OS layer, the UDP packet arrives. OS looks up which process bound to. We have UDP 443 and IE chrome.exe, then nix-quick, then CADI. Application layer, QUIC handles streams, congestion control, encryption, TLS 1.3, session recovery. On top of QUIC sits HTTP/3. So QUIC just changes how TCP responsibilities are implemented. But OS routing still uses IP plus port plus protocol. Cloud routing still uses CIDR plus firewall rules. Putting it all together in a full cloud app, Azure example, imagine your app, Angular frontend to ASP.NET API to SQL database. Traffic flow. From internet, Azure App Service, user open browser, second browser request through https://myapp.azurewebsites.net. Azure Edge routing, we check DNS, then load balancer forward to the app service. If HTTP/3 enabled, QUIC UDP 443 is used. If not, falls back to HTTPS TCP 443. Inside app service, the OS receives packet. OS looks up. We have UDP 443 for QUIC delivered to Kestrel. Kestrel handles HTTP/3 on QUIC. App connects to SQL. Your backend opens an outbound TCP connection, like 10.0.2.4:1433 to SQL database. Azure routing sees 10.0.2.0/24 is the database subnet. Then it forwards the packet there. Inside SQL Server VM, OS does TCP 1433 to SQL Server process. Exact same idea as NetStat. Key insight: locally, Windows uses protocol plus IP plus port to process lookup. Then for cloud, Azure uses CIDR routing. It sends to the correct VM/app. Then inside the VM, protocol plus IP plus port to OS to correct process. QUIC still uses UDP ports, usually 443. So same OS routing, same cloud routing, different transport mechanics handled in user space. Final summary in one sentence: your Windows Netstat output is literally the same mechanism used by Azure and all cloud platforms, just wrapped in additional layers of routing, CIDR based, and firewalling, and Quick still fits perfectly into that model because it just binds to a UDP port like any other protocol. First, on top of Quick sits HTTP/3. What does that mean? Think of the network stack like layers. Application layer, HTTP/3, transport layer, Quick, internet layer, IP, link layer, Ethernet/Wi-Fi, hardware layer, NIC, antennas, PHY, which sends the signal to the Wi-Fi. Quick equal transport layer. Quick plays the same role as TCP or UDP. It handles connections, reliability, packet loss recovery, encryption, TLS 1.3 inside Quick. HTTP/3 equal application layer. HTTP/3 is the actual protocol used by browsers and web servers. It uses Quick instead of TCP. So when someone says HTTP/3 sits on top of Quick, they mean Quick carries HTTP/3 messages the way TCP carries HTTP 1.1 or HTTP/2. So yes, Quick is closer to the networking layer IP, while HTTP/3 is closer to the application layer. Second, why is Quick considered close to IP? Because Quick packets are wrapped directly in UDP. We have Quick packet to UDP to IP to Ethernet/Wi-Fi. So data flows like browser HTTP/3 to Quick to UDP to IP to NIC hardware. Why is there an OS involved? Why protocol plus IP plus port? 2OS is the correct process instead of protocol plus IP plus port plus process lookup, because the OS owns the network card. The network card does not know which application should receive packets. It only knows how to send or receive frames. So the pipeline is NIC receives Ethernet frame, then to interrupt sent to OS kernel, then kernel networking stack process frame, then kernel looks at IP address, protocol UDP or TCP or Quick, then port. Then kernel delivers data to correct process socket. Applications themselves never talk directly to the NIC unless doing raw NIC bypass like DPDK. Why does the OS needs to be there? Because the OS is responsible for managing hardware, enforcing process isolation, security, routing, socket ownership, firewall rules, not processing, packet scheduling. If process talk directly to the NIC, one app could steal another app's data, prevent others from getting packets, bypass firewall, flood the network. So the OS is the traffic controller. Linux versus VM case. Protocol plus IP plus port. 2OS correct response refers to a normal OS. Inside a VM, it becomes packet, host OS, hypervisor, or kernel networking, to VM virtual NIC, to guest OS to process. So there may be two network stacks involved. Bare metal OS to virtual NIC or hypervisor to guest OS to application. What actually happens when a packet arrives? NIC hardware gets a frame from a wire or radio, places it into DMA buffer or direct memory access buffer. So it puts that into the memory of the operating system of that one that has NIC, and that memory will trigger an interrupt to the CPU. For in OS kernel, it reads frame header, then it validates checksum. Third, looks at ether type, IE 0x0800 for IPv4. Fourth, looks at IP protocol, 6 equal TCP, 17 equal UDP. Fifth, looks up socket, Then we have protocol, comma, destination underscore port, then local underscore IP. 6. Copies payload to the application's socket buffer. 7. Wicks the application. EPOL, comma, select, comma, IOCP, etc. Application, your app finally receives the data. In Quick case, Quick lives in user space, not kernel space. So flow is NIC to OS kernel, to UDP socket, to Quick socket library, to HTTP/3 application. This is why Quick can be updated without OS patches, unlike TCP. Visual diagram, application, HTTP/3 to Quick user space transport to UDP kernel, to IP kernel, to Ethernet/Wi-Fi driver, to NIC hardware. Final answer in short, does HTTP/3 sit above Quick? Answer yes, HTTP/3 uses Quick just like HTTP/1.1 uses TCP. Is Quick closer to IP? Yes. Quick runs over UDP, which is directly above IP. Why involve OS? OS controls NIC access, routing, firewall, socket ownership, scheduling. So as you can see, OS still take over all of this layers control, including the socket, the NIC access, the routing, the firewall, socket ownership, scheduling. Why not direct IP plus port to process? Because only the OS safely knows which process own which socket. In a VM, packet goes host OS to virtual switch to guest OS to application. So Angular, React, iOS, Android apps do not see sockets, IP headers, UDP/TCP numbers, Ether type, or NIC hardware because those are from OS or the router's OS. They call fetch function or WebRTC slash etc. and the OS bus browser handle everything underneath. So let me explain layer by layer. Does Angular call HTTP/3 directly? Not exactly. What Angular actually does when you write fetch argument code https://example.com/data Angular to browser networking stack to OS. Then browser decides the transport. If the site supports HTTP/3, browser :HTTP/3 to Quick to UDP to IP to Ethernet/Wi-Fi. If the site does not support HTTP/3, browser :HTTP/2 to TCP to IP to Ethernet/Wi-Fi. Angular never chooses Quick or TCP or UDP. The browser decides based on ELPN negotiation during TL's handshake and server support. Does mobile Gradle use Quick? No. Gradle, Android build tool, has nothing to do with networking. Android apps use OS networking libraries, Java/C++. Web views and Chrome implement Quick internally. If you write URL argument code https://example.com.read text function, Android OS decides if Quick is supported, whether UDP is used, how sockets are allocated. Where is the socket created? Sockets are created at the OS level. Web apps and Angular do not call socket APIs. They do not choose ports, do not open UDP or TCP explicitly, cannot see Ethernet or IP headers. Instead, the browser does socket = create UDP socket for Quick or socket = create TCP socket for HTTP/1.1 or 2. On Linux, we have intfd = socket argument af_enet, sock_dgram, iproto_udp. On Windows, we have socket argument af_enet, sock_dgram, iproto_udp. On Android, bottom -most, Java/Kotlin to JNI to C to kernel socket API. Angular never touches this. Can Angular see IP protocol? 6 = TCP, 17 = UDP? No. A browser sandbox prevents reading raw IP headers, seeing protocol numbers, Inspecting Ethernet frames, accessing NIC hardware. This is for security. Website cannot sniff packets, they cannot build raw sockets, they cannot bypass firewalls. Only native OS kernel does that. Who looks at ether type, protocol, ports? NIC reads example Ethernet header colon dest MAC, then SRC MAC, then ether type equals 0x0800 IPv4. This is processed in network card firmware, Linux slash Windows driver, kernel networking stack. Kernel reads IP header like this: protocol equals 6, which is TCP, protocol equals 17, which is UDP. Kernel socket table, it reads local IP, port, protocol, the process or browser socket. Browser then delivers to JS runtime, which hands data to fetch function callbacks. Angular never sees NAT, UDP or TCP numbers, routing tables, checksum, verification, hardware interrupts, DMA buffers. Why can't Angular read sockets? Because JavaScript in a browser has no syscall access, runs in a sandbox, is restricted to Web API only allowed high-level calls, fetch function, XML, HTTP request, WebSocket, WebRTC. Everything else is hidden for safety. Can any browser code see raw sockets? No, for security. But if you install a browser extension with permission, you can sometimes inspect more. If you use WebRTC data channel, it still doesn't give you raw UDP, but quickish behavior flows through. If you want raw packet access, you must go native. See Linux raw socket, winpop/np cop, eBPF, DPDK, kernel modules, Wireshark. That's why Wireshark can see packets but Angular cannot. What is the socket lookup actually? When a UDP/TCP packet arrives, OS kernel maintains a table like IP, port, protocol, owning process socket. Example, UDP 10.0.0.5:443 belongs to chrome.exe tab, number 21. Then kernel wakes that process, data passed to socket buffer, browser decrypts/processes, then Java script callback fires. Visual stack of Angular fetch, your Angular code, then to browser runtime, to HTTP/3 encoder, to quick transport, to UDP packet, to IP packet, to Ethernet frame, to Wi-Fi card, radio signal, to access point. So that's the AP we're talking to internet. On the return path, we have NIC receives bits to DMA, direct memory access, to of the OS. So as you can see, OS plays a large part. Then it will tap into the kernel, to UDP socket, to quick, to HTTP/3, to browser. So that UDP socket, its connection on the table, it will now connect to the quick, to HTTP/3, to browser, to JS promise resolved. At no point does Angular touch the NIC, parse UDP, see headers. Final answer. Question, does Angular calls HTTP/3? No, it calls fetch function. Browser chooses HTTP/2 or HTTP/3. Does Angular call quick? No. Browser's networking code does. Does Android Gradle choose quick? No. OS networking stack does. Who creates sockets? OS kernel via system calls. Who reads Ethernet/IP/UDP headers? NIC hardware plus OS driver plus kernel networking stack. Can Angular see protocol 6 TCP or 17 UDP? No, it's sandbox. Can browser see ether type 0x0800? No, only packet sniffers or OS kernel can. So we're going to decode everything and connect all words together. How NIC filtering and multicast or broadcast reception works. How this connects to turn/WebRTC/quick. How the laptop Lenovo Windows NIC sends or receive frames. Whether this is signals in Wi-Fi and how code turns into signals. What actual code looks like. Driver, OS kernel, firmware, not C. How turn or ICE relates to what your NIC is doing, why it matters, how often people hit turn relays in real world, how this affects you on your home router, how to see all this working on your OS, how to visualize it using your big integrated mega diagram. First, NIC to CPU and CPU to NIC. Your laptop, network card, Wi-Fi or Ethernet is a hardware packet mailbox. When sending a frame outbound, first, your app, Chrome, WebRTC, Quick, etc. writes data to a socket. 2. Kernel network stack. Second, kernel, TCP or UDP or IP layer. It builds packets IP, UDP, DTLS, turn, SRTV. Third, driver formats them into layer 2 frames. Ethernet header, destination MAC, optional VLAN tags, CRC. So those are the frames options we discussed in the previous video. Fourth, NIC DMA transfer or direct memory access transfer. The OS gives the NIC a pointer to a memory buffer using DMA, direct memory access. Fifth, NIC converts the bytes to VHY signal or PI signals. If Ethernet, it means it's for voltage changes. If Wi-Fi, it means for QAM modulated radio waves. There's no C, no if-else loops. The closer you are into the hardware, the less code you see or the less if-else you see. This is written in OS kernel code C, driver HAL C, NIC firmware C/HDL, hardware state machines. When receiving a frame inbound, wireless or Ethernet RF PHY decoding. Second, NIC checks. CRC, okay, question. Second, MAC destination matches. Inside it, my MAC, question. Inside it, broadcast FF:FF, question. And then inside it, multicast table, question. So it checks if it's my MAC or broadcast or if it's a multicast table. So this is in the NIC checks. If NIC is promiscuous mode, everything. So in NIC we have CRC and then MAC destination. That's where the broadcast and multicast fits in. Then third, if accepted, DMA to RAM. So if NIC accept that, it means the frame is good to go. Then that's the time it will direct memory access to RAM. And then fourth, driver interrupt. It will interrupt the driver. Then the driver will now hit into the kernel. And then the kernel, fifth, we have IP packet filtering. So if it passed the IP packet filtering, it will go into 6 UDP/TCP filtering. This is also will create its own socket. And then 7, delivered to socket and then delivered to application. This is exactly matches what your multicast textbook meaning. NIC filters first, then driver filters, then IP filters, then UDP port filter, then app receives. So as you can see, we have multiple level of filters. NIC filters based on MAC, destination, multicast, broadcast, then IP filters or driver filters, and then IP filters. So for driver filters, as we can see, that's a direct memory access. If that frame could actually enter that direct memory access for its RAM and in turn to the CPU to kernel system call. For IP filters, we know that it's on the layer 3, so we are able to filter it depending on the header on the layer 3. But for this layer 2, there's also header, right? So that also pertains to this the driver filters and NIC filter first. Then after IP filter, we have also UDP port filter, which we're gonna discuss in the future video, and the app receive. But sometimes the app has a filter as well. How Wi-Fi signals are produced in code. your software never generates waveforms. What actually happens, up to socket to kernel, network stack to driver to NIC firmware to DSP to RF output. Code example, kernel sending an Ethernet frame in Linux. We have dev underscore q underscore xmit argument struct t space sk underscore buff asterisk skb. That eventually caused the NIC driver ring buffer submission. Something like tx underscore ring argument head equal dma slash map underscore map underscore single argument dot semicolon. Then we have write tell argument tx underscore doorbell comma nic register semicolon. At that point, hardware takes over, not software. Inside the NIC, hardware does scrambling, convolutional slash FEC encoding, COM modulation, BPSK, QPSK, 16/64/256-COM, OFDM carrier generation, RF amplifier output. This is not CN, not if else. It is fixed logic gates, microcode, DSP pipeline. So we discussed this in the frame chapter in the previous video. How this relate to turn or ICE or quick or WebRTC? Turn slash WebRTC slash quick run far above this. So it's in the since this is layer 2, those things are in layer 4. So it relates in transport protocol. So relationship vertical stack. We have up WebRTC API to DTLS slash SRDP slash quick to UDP to IP to Ethernet slash Wi-Fi frames to NIC driver to NIC hardware to radio signals or wire voltage. When WebRTC sends a allocate, create permission, channel bind, send indication, they eventually become UDP packet. Then after that, inside that UDP packet will be inside IP. So as you can see, we have that protocol first that becomes UDP packet, and it's abstracted again from the router as we discussed in the previous video. So the router will only see UDP packet, and then it will feed that inside IP datagram. Then in an IP, it will feed that inside Ethernet or Wi-Fi frame. Your NIC doesn't know or care that it's turned. To the NIC, a turn packet is bytes in memory to transmit. So it only cares if it's destination MAC or the multicast it is sending to a multicast address or broadcast address. How turn connects to your multicast filtering? The textbook explain NIC receives network frames, decide whether to accept them. Turn slash web RTC are built on UDP. So before a turn packet reaches CHROM slash web RTC's ICE agent, it must pass first NIC hardware filtering. So if it doesn't accept the multicast or broadcast of that NIC hardware and driver, and then the second is NIC driver filtering. If it doesn't pass that, it won't go to its destination. Third, IP filtering. Fourth, UDP port match. Fifth, delivered to WebRTC stack. That's how they are related. If one of those denied along the path, it will not go to the destination. Why turn or relay is important in real life? WebRTC connection success rates, 60 to 70% of users connect via stun, direct. 30 to 40% fall back to turn relay. Inside that, we have symmetric NAT, DS Lite, CG NAT, bad firewalls, coffee shops, or hotel Wi-Fi. So coffee shop and hotel Wi-Fi kind of like similar to CGNAT now because it kind of have more restricted hardware. That's why they use rare. So turn is not rare. Quick is also UDP based, similar NAT problems. Google Chrome telemetry, 8 to 10% of quick sessions break without fallback. So you may use quick, but if you don't have fallback like turn, you won't be able to handle the important session or that crucial fallback. So WebRTC solves this using turn. How you use this at your home. Converge typically uses carrier grade NAT or DS Lite or NAT 444 in some regions. This means direct stun is often blocked. Turn is required. So if you use WebRTC video calls, Google Meet, Messenger, Zoom Web, played Stadia, NVIDIA GeForce Now, used web torrent streaming, used Discord voice on browser, you likely hit turn relay. So how to see this happening in your OS? So when you call in Discord, try to run this in CMD. Netstat space dash ano, vertical bar space find code 3478 ports 3478 equal turn 5349 equal turn slash TS 443 UDP equal turn over TS tunnel. To see live packets, you have Wireshark to UDP and stan. So if you use this in Wireshark, UDP and stans, you're gonna be able to see this in real world, how the packet actually work in the whole system. Now you'll see allocate request, allocate success, create permission, channel bind, send indication, data indication, because those are the properties that we can see in Wireshark for turn protocol. Now Linux Wi-Fi NIC statistics, we can use ETH tool space dash capital S space WLAN 0. It will see RX drops, CRC errors, multicast or broadcast counts. To see multicast joins, you can use this netstat-gn. To see raw NIC frame arrivals, we can use TCP dump space dash I space WLAN 0 space dash E. The dash E prints Ethernet header like this, FF colon FF colon FF etc., which is for broadcast. Then 01 colon 00 colon 5E colon XX etc. for multicast. So that's how we see that multicast and broadcast in the actual NIC. We don't see that in just UDP ports we can see in Netstat. Those are in the transport layer or in the IP, because those are in the second layer. To be able to see this lower layer, you will need the Wireshark. Or I mean, you can also actually use that. I think you can do this in Windows as well, TCP dump-IWLAN0-E, but it doesn't have as much details of the actual broadcast and multicast MAC frame for layer 2 as Wireshark. How to visualize this in Mega diagram? So for application layers, we have WebRTC, iSTAN, Turn, DTLS, SRTP, UDP, IP. Then packet structured in software 2, OS/kernels, UDP demultiplexing. So that's how it demultiplex the DC UDP, and it will create a socket for the application to invoke to the JavaScript fetch. Then IP filtering, NIC driver DMA rings to NIC hardware, frame filtering, CRC check, MAC accept/reject, DMA to run to PHY/radio. In here, we have COM modulation, OFDM, 802.11 preamble, RF transmission. So these more lower layer are designed to be resistant to failure. That's why we don't see any. We need to work around these limitations of hardware, and it is being designed by electronics or their electrical engineers. So COM modulation, OFDM, that's why once it works, you know it works because it consists of a larger theory of electrical and electronics behind it. So final summary, how does your NIC send frames? Kernel build packets, driver writes DMA descriptors, NIC hardware transmit over RF or wire. Is Wi-Fi signals? Yes, DSP and the NIC convert bits to modulated RF. Is it C, if else? No, mostly C in OS kernel, firmware, microcode, hardware state machines. How does this relate to Turn? Turn packets still must arrive through NIC hardware, pass filtering stocks before WebRTC sees them. Why is it Turn important? 30 to 40% of users need it because of NAT, including many on Converge. How did you use it on Converge? Likely daily without knowing. WebRTC falls back silently. How to see it? You can see in Wireshark using stun filter, netstat, port usage, TCP dump, raw Ethernet headers. So another thing is TCP dump is how you actually see these headers in layer 2. So the key is headers to be able to see these multiple layers. ETH tool/netstat NICStats. So here we have WebRTC.js API to turn packets to UDP/IP to NIC DMA to Wi-Fi modulation layer. So let's build a very simple but realistic visualization of the whole chain from your browser to OS to NIC to Wi-Fi radio to access point to internet. When your laptop sends a frame, what is the chain? We have Chrome or Firefox or Edge user app to Windows WinSock API to TCP or UDP stock kernel networking to IP to Ethernet/Wi-Fi encapsulation to NIC driver or kernel to Wi-Fi hardware radio/modem to air 2.4 GHz or 5 GHz or 6 GHz to your router/AP. Where is the code that sends the frame? It lives in the OS kernel plus NIC firmware. On Windows, packet creation and routing equal kernel C code TCP/IP.sys. In NIC driver equal compiled C code in kernel mode. In NIC firmware equal binary firmware in the chipset. No C, #, no.net. This is low level C controlling hardware registers. What actually happens when packet leaves? Let's say Chrome needs to send a TCP packet to 142.251.170.188:5228. You actually have those connections right now. Google services, browser call WinSock, send argument socket, data, dot. Then second, kernel builds a TCP segment. We have Ethernet header, then IP header, then TCP header, then data. The NIC driver writes to the card's TX string buffer. Driver writes packet to DMA memory descriptor to hardware, says it. Fourth, NIC firmware transmitted out of the antenna. The Wi-Fi chipset converts the packet to OFDM symbols, modulation to radio signal. That is, the ones and zeros become phase plus amplitude changes in radio waves. How does it reach the CPU the other way? For received packets, we have antenna receive signal, Wi-Fi chip demodulates it, to NIC firmware raises an interrupt, to ring vapor DMA kernel networking stock, to TCP reassembly, to application receives data in recv function. So how does broadcast look in hardware? When your laptop needs to send, we have MAC:FF:FF:FF broadcast. There's no routing logic. The NIC simply sends out 1.802.11 frame. Then every device on the Wi-Fi hears it. No ARP needed because ARP is only required for unicast. For example, 192.168.182 WUHAS to ARP to get SMAC, but broadcast already has destination MAC. We have FF:/FF:/FF:/FF:/FF, so the OS doesn't need to perform a lookup. So it already has the MAC, it doesn't need the IP anymore. Why no mapping required? Broadcast equals send to everyone. The NIC treats broadcast frames specially. That backs into the factory level. It is built or binded in the factory level to see that as a broadcast address, and also its own MAC are burned into the factory. So it always transmit, it do not check destination equals my MAC. Unicast requires DST MAC equal my MAC. Broadcast does deliver to host regardless. 7. Is broadcasting using ICMP or UDP or something else? No, of course, because it's in layer 2. Broadcast is just a MAC address behavior. Above Ethernet, it can carry anything. Right? After it does send the frame, it can carry anything. It could use, for example, TCP doesn't use broadcast because it's connection oriented, but UDP can use broadcast. ICMP can use this as well. DHCP can use this. ARP can use this. So most protocol can use this. So ARP is for ARP request. DHCP is for DHCP discover. ICMP is for ping broadcast, like our example. UDP MDNS 5353 for TCP, no TCP broadcast. So the example, Ethernet broadcast FFFF, then IP broadcast 10.0.0.127, and ICMP echo request, because as you can see, ICMP can use broadcast. So yes, ICMP over broadcast is possible. Does NIC know all MACs on Wi-Fi? No. NIC hardware only stores your own MAC, multicast group MACs, broadcast MACs. So that's how we checked earlier. So there's kind of like an if-else in NIC to be able to see this around this group. Its own MAC, multicast group MAC, destination MAC, source MAC, broadcast MAC. Some NIC support Prometheus mode, like Wireshark snipping for normal operation. NIC only forwards relevant frames to CPU. Everything else is filtered by hardware for performance. How much of world traffic is broadcast or unicast or multicast? Approximate real-world numbers. Internet backbone, global, 99.9% unicast. Broadcast is not routable across the internet. Multicast is less than 0.1%. Home or Wi-Fi LAN, 95 to 98% is unicast. 1 to 3% is broadcast or multicast. Typical LAN broadcast examples are DHCP Discover, MDNS 5353, Windows Network Discovery. So those are the common broadcasts. So when you use DHCP on your router, you're using broadcast. When you use ARP, you're using broadcast. When you're using WND, you're using broadcast. Or MDNS for discovery of DNS or MDNS 5353. So even at home, most traffic is unicast, TCP or QUIC or UDP. Also, this MDNS use UDP. So whenever you're trying to find DNS, you're actually using the UDP. Where in the code does broadcasting broadcast handling exist? Windows networking stack. Packet creation, TCP IP.sys, Ethernet layer, NDIS driver, device driver, OEM NIC driver, Intel/Realtek/ATC. In the NIC firmware, there are literal logic checks like this. If DST_MAC equal FFFFFF, accept -frame function semicolon. Else if DST_MAC equal my MAC, then accept _frame function, else draft_frame. Not C, but low-level firmware or synthesizable hardware logic. Signal in air. What does NIC really output? Wi-Fi uses OFDM 802.11a/g/n/ac/ax we discussed in the previous video. Bits are encoded as broadcast symbol maps to QAM constellation points, baseband modulated into radio frequency, sent out at 2.4 GHz/5 GHz/6 GHz. Your software never sees radio waves directly. It only sees digitized frames after the Wi-Fi chipset demodulates them. So your laptop in Bulacan use this. If your DHCP client sends FF:FF:FF, then with an IP 255.255.255 with a UDP 68 to 67, then the flow is Chrome not involved, Windows DHCP services is involved, to TCP.IPsys builds UDP packet, to Ethernet layer sets DST_MAC equal FFFF. So your Windows do that, sends UDP with an Ethernet layer destination MAC FFFF to its NIC driver, writes into the DMA ring. Then this DMA ring will go to Wi-Fi chip, modulates into radio. Then AP receives it. Then AP CPU forwards to DHCP server. So let's see. So how your laptop is running in Windows 11? Like sends a broadcast frame over Wi-Fi or internet, how the NIC driver kernel and code layer works, how this relate to NetStat or UDP or TCP connection we saw, how this relates to QUIC versus UDP or TCP stack, how the routing table applies, how real radio signal come into play, and a single mega diagram trying everything together. So, short answer, yes, you're experiencing normal abstraction shock of networking because everything happens in layers that are not visible at once. You're intuitively trying to connect kernel code, NIC driver, radio hardware, routing, packets on wire, processes and ports, real machine behavior, and most textbook explain them separately. So this answer will merge them visually into one unified life of a packet diagram. How your Wi-Fi or Ethernet driver actually sends a broadcast frame. In your machine, the flow is from application DHCP client to send broadcast to Windows socket API, which is the WS2_32.dll to Windows TCP or IP kernel stack, IP plus UDP, to NDIS network driver interface, to Wi-Fi NIC driver device specific, to NIC firmware plus DSP plus RF hardware. OFDM radio signal to OFDM radio signal at 2.4 or 5 GHz. The DHCP discover broadcast like Ethernet destination MAC equal FF FF, which is the broadcast. Source MAC equals your NIC MAC. Then the IP, source IP equals 0.0, so you don't have one yet. That's why you're asking or you're trying to discover the private IP you have from your router. Dest IP equal 255.255.255, so that's a broadcast destination IP. And then the UDP in transport, so we have source port equals 68, which is you, your client. Dest port equals 67, your server, which is the router. Then the DHCP payload. So wait, how does the NIC know how to output radio waves? Is this if-else code? No. Below layers exist high-level kernel implemented in C. UDP transmit function builds the packet. IP layer wraps the frame. Function calls go down to NDIS. So the UDP transmit the function and it builds the packet, and then it encapsulates in IP layer, it wraps the frame, and then the function goes down to the NDIS. So it's thus in layer 2 to layer 1. Then the driver layer still C, it maps OS send calls to NIC instructions. Then in NIC firmware / hardware, not C, not if-else. This is ASIC logic, DSP, digital signal processor, and microcode. These handle OFDM modulation. So this is kind of like in the hardware level, sending it to Wi-Fi when you're trying to discover your address using the DHCP broadcast. So this handle OFDM modulation, COM, QAM, symbol mapping, RF timing, retries, VHY coding. So radio transmission simplified. So how this works is ones and zeros, to group of bits, it mapped to QAM symbol points in a complex plate, to OFDM modulation, to converted to analog electrical signal, to RF oscillator pushes this into the antenna. Then it pushed to energy propagates through the air. Your operating system never see this radio wave. So that's important. That's happening outside of your operating system. Then once that happened, the Wi-Fi router, it will receive sample DSP demodulates to NIC driver, to its OS, to its application, and then it will return back to you the actual private IP address. So wide broadcast needs no ARP. ARP is who has this MAC, but for broadcast, destination MAC equal FF:FF already, meaning send to everyone, no lookup needed. NIC already knows that FF:FF:FF means flood the LAN. So no ARP, no mapping, no per host resolution. So how does NIC deliver frame back to CPU? Incoming frame, follow the reverse path. Antenna receives RF to RF front end, down converts to DSP, demodulates OFDM to NIC firmware, reconstruct frames to NIC, puts packet in receive ring buffer, DMA, direct memory access, to NIC interrupts to CPU, to Windows TCP or IP stack, processes frame, Two applications receive data. DMA means NIC writes packet directly into memory. CPU isn't copying every byte, just like we discussed in DMA in the previous video. How does this connect to the netstat window? So the screenshot shows many UDP listener like UDP 0.0.0 colon 5353, UDP 0.0.0 colon 50557, then UDP 192.168.1.47 colon 1900. Each line means a program is saying, if an incoming packet arrives addressed to this IP, port, deliver it to me. When a packet arrives, NIC receives frame, Windows Network Stack decodes, look up IP plus port, then it finds process, then delivers payload to that process socket. Quick fits in here. We have application, then quick, user space protocol, then UDP, then IP, then NIC, then WAR. Quick is encrypted, reliable, runs on UDP, implemented in user space, not kernel. This is why netstat-ano-p UDP will show many quick ports from Chrome and Edge. Why Unicast dominates the internet. Internet backbone. Unicast is greater than or 99.9% of the traffic. Broadcast 0%. Multicast less than 0.1%. Broadcast doesn't scale globally. Routers drop them. Home LAN/Wi-Fi 95.98% unicast. Web, quick, TCP, DNS replies 1 to 3% broadcast. ARP, DHCP discover, net bias 0 to 2% multicast. MDNS 5353, IPv6, ND streaming. So your machine sees ARP, DHCP, MDNS, CSDP, Windows discovery. So the machine or the laptop constantly see this ARP, DHCP, which all broadcast, right? Broadcast, multicast, MDNS, SSDP, Windows discovery. So your laptop constantly see broadcast and multicast. So this is normal. Full mega diagram, life of a DHCP broadcast frame from code to radio to router. We have application layer, Windows DHCP client, DHCP-S, vc.dll, call send to function with destination 255.255.255.255:67 to Windows TCP or IP stock kernel. Inside this, we have UDP header created, SRC68 to DST67. Then we have IP header created 0.0.02 255.255.255.255. Then we have Ethernet header FF:FF. Then next, NDIS API, OS hands raw Ethernet frame to NIC driver to NIC driver C code, places frame in NIC transmit ring buffer DMA to NIC firmware plus hardware. Then inside it converts bits to COM symbols and OFDM modulation. Then it sends RF at 5 GHz. Then in air, it's sent to access point, receives broadcast forwards to LAN. Only for the HCP server, it responds unicast, for example 10.0.0.1, your MAC/IP. Then towards to NIC receives reply at DSP, demodulates, stores via DMA, interrupt to CPU. Then towards Windows TCP or IP stock. Then inside we have UDP port 68 lookup. DHCP client gets data. So the one diagram showing all networking on your PC at once. Applications, Chrome, Quick, Spotify, DHCP client, it sends broadcast to Windows Network Stack, TCP or IP. Quick to UDP to IP to Ethernet, Spotify to TCP to IP to Ethernet, DHCP to UDP to IP to Ethernet. And after that, towards to NDIS plus NIC driver, it map OS packets into DMA buffers, and towards it, NIC hardware plus radio VHY. We have bits to QAM to OFDM to RF signal. Then towards, so this is the air, towards router/AP, routes unicast to internet. Then broadcast stays local. So why you feel something is missing? Because networking is invisible when working correctly. You're trying to create a unified mental model. Real systems divide work across 7 to 10 layers. Most book explains them separately. You're doing exactly what network engineers do. I need the whole thing in my head at once. That takes months or years, and you're moving very fast. Visualization helps, and diagram, like the one above, are the key to completing the mental model. So if you want final advice, if you want to see all this happening live, install on Windows Wireshark and pick up Capture Interface Wi-Fi. Then watch the HCP ARP Quick DNS LAN broadcast. You'll suddenly see, oh, this was what's happening inside the radio, and everything snaps together.